Yeah, it's great to be here. It's a lovely conference, really well organized. So I'm Raphael, and I'll be talking about my experience building synthesizers live in OCaml. So this is both for actual performance, so that means that I'm doing it in front of an audience that is hoping to enjoy some music. But I'm also doing it by myself, just to play with synthesizers interactively with a low iteration cycle, so that I can test many things in a shorter span of time, while also making use of the abstraction of functional programming so that I can have a concise way of specifying things. So this is briefly the roadmap for my talk. I'll give some motivation, some background, some context on why I'm doing this. Then I'll talk about my DSL to build synthesizers in OCaml. I'll give some examples. The examples are mostly what would be someone's first steps in general if they are starting to work with digital audio synthesis. Then we'll go into a little bit how this is compiled to the underlying rendering engine language. Then we'll speak about how I'm controlling the synthesizers with concurrent processes, and a little bit of what I'm thinking to do next. This is very much ongoing work. I think I started it last year. There have been a couple of performances and jams with friends to some level of success. Yeah, so this is me. I'm a musician and a software developer. In practice, this means that I do software development by day, and by night, I complain that I don't have enough time to make music. But to actually give you some context, I need to go back a few years. So back in school, I studied music composition. And around the same time, I started gigging as a software developer. I think there's a bit of a lesson here. But anyway, so when you start composing music, you also start interacting with music software. And this can be a score editor, so something like, if you haven't interacted with one, this is like a word processor, like Microsoft Word, but for music notation. So it's pretty useful, gets you editing scores much quicker than you could do by hand, and much more, with a more consistent output. There's also audio editors so that you can shape audio files and cut and splice and do things. There's also digital audio workstations so that you can do larger projects where you're applying synthesizer effects and grouping things together. And the thing is that all these programs are pretty great. I use them really often. But at the same time, I felt that I needed something more. More in the sense of something different, not necessarily something better. And how I felt at the time was that the software all make decisions for me. So they have baked-in assumptions. They make some things easy, some things hard. And that, in a way, affects how I approach writing music. And I felt my intuition at the time was that I need to take control of this. I need to sort of take a step back and think about how I want to do music. Once I started getting more acquainted with the programming pop culture, I realized that this has a name, so it's not invented here. I joke, but back then, this was one of the things that motivated me to get deeper in programming than what I had done up to that point. And my intention wasn't to write a better score editor or a better audio editor, but to be able to, every time I was writing a new piece of music, to be able to ask myself, what assumptions do I want to bake in to the tools that I'm using to make the music? How do I want to express myself? And then make the tool that could help me do that. And an example of a type of music where the need for this becomes clear is using a sort of loose term of process-based music. So let's say as an example that you have a piece of music that gradually changes harmony from point A to point B, or changes a rhythmic pattern from point A to point B, and that's your listening experience. That's what you want your listeners to pay attention to. If you're writing this type of music and you're writing note by note, what it feels like, and that's maybe an analogy that I think the programmers will understand, is that it feels like you're manually compiling your high-level specification that you had to a low-level language, and you're writing them note by note. You're thinking in terms of patterns that are evolving or harmonies that are changing, but you're sort of forced to write down note by note, which is not necessarily wrong. A lot of great music was written like this and will still be written, I'm sure. Nevertheless, as functional programmers, I imagine that you can sort of understand that sometimes it's nice to have a language that sort of matches your domain of thought. Some renowned composers also seem to share, let's say, the same sentiments or the same enthusiasm regarding using computers for composition. So that was validating to me. And a big point for me was having some contact with Common Lisp. So maybe that's not common knowledge outside of the niche, but it has a really consistent and important presence in the music and computing field. So there are a lot of important projects that are programs that are used to this day that were written in Common Lisp. An example is Open Music. And that's how I got in contact with functional programming. So that was already a big thing for me. But it was also important because I saw people in the community saying that in Lisp, you sort of grow your language to match the problem that you're working with. And that sort of spoke to me in the sense that it was, in a way, what I was looking for. So I used it as my default, my go-to language for a while for my personal projects. For whatever reason, I started branching out and I hopped around, used a bunch of other things, and eventually settled on OCaml. I must say that I still miss sometimes the level of interactivity that I would get with Common Lisp. And in a way, this project is sort of trying to regain that in some small aspect. The last bit of background that I want to give is the idea of live coding. So I was already used with the, let's say, programming interactively because of Common Lisp. Live coding takes that to a next level and makes that as a performance. So what that means is that you're sitting in front of an audience with your computer, and you're basically programming algorithmic music in front of them. Usually the screen is shared so they can see what you're coding. I'm mostly in it for music, some bit of visuals, but it's not constrained to that. People have been mixing live coding with all types of performances, with dance, with new media. So someone is sort of, as a performance, they are manipulating a website or something like that. It's a very interesting type of performance. From the programming perspective, something that I find interesting is that the constraints of this medium really shift the way you think about programming. Because usually we're here to take into account maintainability and how you're going to understand your code 6 months from now, how your teammate is going to understand your code. But in this context, your code is not going to survive the night. So it's more like a one-off script that sometimes you need to do to fix things. But unlike that script, you do have outages. Like in that script, you can run it once. If it doesn't work, you fix it, then you try again, then you fix it until you sort of converge to the right solution. Here, you might get no sound, and people are looking at you and waiting, and they want to dance. So it's interesting how it shifts a little bit how you approach programming. Yeah, so getting into the sound synthesis part. A disclaimer is that I won't go that low level into sound synthesis and sound signal processing algorithms. But in general, if we want to generate sound waves or make sound from a computer, we need to move its loudspeakers. In order to do that, we need to send a stream of numbers to what we call the digital to analog converter, sitting in the sound card that will convert the digital to the analog and eventually push that loudspeaker so that sound is produced. And in order to do that, from OCaml, I started writing this library. It basically has an embedded DSL, domain-specific language. It carries forward the tradition of having a separation between instruments and events. So this is a tradition that is common to sound synthesis systems and programming languages. So that basically means that you have a way to describe synthesizers or instruments that have parameters, say a frequency, an amplitude, or I don't know, a reverb. And later on, you have a separate function call or a separate syntax to instantiate that instrument with certain parameters, and that will emit sound. So what that means in practice is that your language, and in this case my DSL, is not really describing sound. It's describing sound generators or signal generators. And then there's a separate API call so that you say, okay, get me this sound generator with these parameters and make some sound. That can be done in real time for interactive applications and usage, and also for offline rendering. And no sound synthesis is done by OCaml specifically. We use Csound as a backend. Csound is at this point rather old sound synthesis programming language, sound synthesis language. But it is really powerful and has a really good community. It's fully open source. It's used as well for as a sound synthesis engine for certain mobile applications and stuff like that. Yeah, so maybe my first example on how we would make sound from the library. So this is a little bit of OCaml. There's a little bit of boilerplate at the top. We can ignore it for now. The thing that we care about here is the synth block. So it's basically saying, giving some configuration to the synthesizer, defining a single instrument called demo for demonstration. There's an empty array, meaning that it has no parameters. And the only thing that it does is basically output a sine wave with 440 cycles per second. So let me quickly evaluate it. So that's done. And as I said just now, there's a separate call to say, okay, now play this instrument. So now I'm saying play the demo instrument from point 0, that means now, for 2 seconds, and with no parameters, because the instrument takes no parameters. So that's basically what it sounds, how it sounds. Okay, that's anticlimax. I think the audio maybe has dropped down. Yep, just a second. Yeah, so this is a sine wave. It's basically possibly one of the simplest sounds that you can make. What I just did was basically I first evaluated the synth block to define the instrument. Then I evaluated the function call to play. Yeah, that was the demo. So this is what a sine wave looks like, the top one and the middle one. The one in the middle has twice the frequency. And the one in the bottom is not actually a sine wave. It's the combination of the two above. So let me demonstrate these three. So if you take a look at the instrument definition, So now I changed it a little bit. So now instead of having hard-coded the 440 hertz, I now have it as a parameter, so it shows up in the instrument signature here. The 440 remains as a default value, so if you don't pass anything, that's what it will get. So let me evaluate it. So now what I'll do is I will evaluate this code that will play first without giving it any parameters, any arguments. So it will have the default value, which was the 440 hertz. And then for 2 seconds, and then it will play for 2 more seconds with the double of the frequency. And so it's a very sterile sound, very, very digital. It's not something that you easily find in nature. So this is my third example here. It's the same thing, but I added this bit. So now I'm multiplying the sine wave, or the signal, the generator that generates a sine wave, by a constant signal with the value 0.2. So what this will do is that it will scale down the amplitude of the resulting signal, so it will be less intense, less loud. So evaluating it. And the reason I did this is that I want to play the 2 sounds together now. So before I played them sequentially, now I'm playing them simultaneously. Okay, so this is interesting. Let me do it another time. So I played them twice simultaneously. I think most of you will agree that you're actually only hearing one sound, like one pitch. So let me do an experiment. So instead of playing the instrument twice simultaneously, let me change the instrument such that I have the original sine wave, which I'm calling main sine. Then I have a second sine wave, which I'm calling doubled. It has twice the frequency. I'm multiplying it by 2. I'm summing the result of the sine waves, the resulting sine waves, and again scaling by 0.2. So now with the some sine waves, I play a single note. And the interesting bit here, maybe it's not news to everyone, but they basically sound the same. And the reason is that because they are exactly the same. So that's something to keep in mind as you start composing the signal generators, which is there's a big psychoacoustics factor. So if you play a bunch of sounds, or if you have a complex instrument definition, you're going to get a complex sound wave. And if that is perceived as multiple sounds or as a single fused sound, depends on the characteristics, the harmonic characteristics, the frequency relations, the sound colors that you're using. And that is something for a composer or for a sound designer, there's something to play with. And that's something that even, let's say, classical composers play with when they're writing for orchestra. So they're writing for there's a string section, but there's also 2 horns playing with the strings, not because the composer wants a counterpoint of melodies, but because he wants to, or they want to enhance the sound or change the sound color in some way. Something else to keep in mind is that parameters are generally also signal generators. But I think to fully understand what that means, or at least to get some ideas, it's worth to look at the types in the library. So this is bits from the code spliced together. So the top type is the type of the actual synthesizer state. The block type means a block of code. You interact with it through a monadic interface. The parameter basically means the result of executing that block. There's a type called expression, so these are non-side effectful computations within this context. And there's a type of parameters, of course. So if we look at the type of for defining instruments, it takes the synthesizer state, so the synthesizer instance to which you're adding the instrument. It takes a string, which is the name of the instrument. Then it takes a block carrying the type unit. So that means that it's a block of synth code that exists only for its side effects. So in a similar way where you have the I/O in high school, and I/O unit means an intuition could be something like that. So the next thing that we see is the outp, short for outpend operator. It takes an expression and returns a unit block. So what it does is basically execute that signal, output it to pend, so in stereo, to your sound card, and gives you a unit block, so something that you only execute for its side effects. And an example of something that would give us such an expression is the sine operator, which basically generates a sine wave. We saw some other operators, so there's one for generating constant signals, so it takes a float. There's one for getting the value of a parameter. And there's this plus and multiplication to combine existing Sino generators. What we have seen already, like the intuition that we have built so far, is that I can use the multiplication to scale a signal. So if I multiply it by something that is smaller than 1, I will make it less loud. And we have also seen that if I add two signals, it's equivalent to playing the two together. Yeah, so let me go through a few examples. So this is my 5th example, which basically goes a little bit further on the previous one. So in the previous one, we summed two sine waves. Now what I'm doing is I'm initializing, so it still has a single parameter for frequency, but what I'm doing is I'm initializing a list of 16 sine waves. They're all multiples of the same base frequency. So so the first sine wave will have frequency x. The second one will have 2x, 3x, 4x, up to 16. What I'm also doing is I'm scaling it down. So as I go higher in pitch, I'm making it less loud, less intense, by a factor of the square of what I'm calling the harmonic index, so the multiple of the base frequency. So I create this list of 16 sine waves, and then I sum them all with a fold, and again I scale it down. So I think before I play this, it's something that is interesting is that ML here, OCaml, is playing its part sort of as a meta language. So is maybe another way to say this is actually sort of like a macro language for the embedded DSL. So this is what it sounds like. So it's a bit buzzy. And the reason is that in comparison with the previous one that was sort of smoother, is that now I'm adding high frequency content to my sound wave, which makes it sound brighter. This may be a good intuition. So what I'll do in the next example to make this more clear is that I added a parameter called buzz. So it controls the levels of buzziness, but in inverse relation. So what I'm doing, can you see my mouse well there? Probably, yeah. Okay, where my cursor is. So now instead of making it, scaling it down by the square of the harmonic index, I'm raising that to the buzz parameter, but everything else remains the same. So what I can do now is, okay, that's evaluated. What I can do now is play a bunch of notes in a loop, gradually increasing the buzz, which that's maybe not intuitive, will actually make the buzz goes down, because that means that the higher harmonics, the higher pitched sine waves will be less present in the resulting sine wave. So you see, as I decrease, let's say, as I decrease the presence of the higher partials, the higher pitched sine waves, we get closer and closer to the original sine wave. Yes. Okay, I have more examples. Okay, this is still the same example. If you look at this here, I'm multiplying the result by a constant factor. Here, I'm multiplying the harmonic index by a parameter. And in fact, all of these, as we saw, they're all expressions. They have the type expression. So in a sense, the type checker would allow me to put a sine wave there instead of a constant. And if the type checker allows it, maybe we should try it. And that's what this example does. But before we play it, maybe we can sort of try to reason about it a little bit. So I introduced this other sine wave here. And if you see at the bottom of the instrument, I'm using it to multiply let's say the sound, the previous example, basically. So instead of a constant factor, I now have the sine wave. So if we go from intuition, I had a constant signal with value 0.2. Now I have a sine wave. So that means instead of a constant signal, I have this sort of wave. I know that in this library, the signals go like by default, they go from -1 to 1. So that's what the sine wave is going. So at its frequency at, let's say, 10 cycles per second, 10 hertz, it's going from -1 to 1. So what I'm doing here in this line is that I'm scaling it to be between 0.1 and 0.3. Because I'm multiplying it by 0.1, and then so that it scales to minus 0.1 to 0.1. Then I'm shifting it 0.2 above. And if you see, the default value in the parameter for the frequency is 2. So it's a very slow sine wave that is within a range that I think is suitable as an amplitude, as a sort of intensity to scale some other signal generator. So what this will give us is something like this. So the volume has a sort of sine wave behavior, sort of like a slow vibrato. The next question that you ask yourself if you're playing with this at home is that, okay, what if I go really high and make a really quick vibrato? What happens? And this is basically what this example does. The instrument remains the same, but now I'm playing multiple notes in sequence, and I'm gradually increasing the frequency of the modulating sine wave. at some point you felt like the kick was going to drop, the bass was going to drop. I don't know how people say it. But it actually took a different turn, right? It became a new sound. So sort of an intuition for it is that as it was slow, we could still perceive it as let's say, curves in the volume. But as it gets faster, the sound wave gets so complex that we start perceiving it. It sort of starts, from the perspective of our perception, it starts becoming a color, like it starts adding harmonic content. And then it sort of fuses in a single sound. So now I'm doing this sort of in a loop, triggering multiple notes. But if I know that I can use signals where I'm using constants, because constants are just constant signals, what I could also do is to use one operator that generates a line, basically. So in this case, it's going from 2 to 300. And this term is an expression that means the duration of the note. So if this instrument is instantiated with a 10-second duration, it will take 10 seconds to do this. And that's basically my frequency, the frequency of the modulating sine wave. So what will happen is that instead of having sort of a discrete notes, this is going to be now a single line. Yeah. What else do I have? Yes. Okay. So as a last example, just to do something different. So what we started with was what we call additive synthesis. So we had very simple sounds, and then we were adding them together to create more complex sounds. Then we started sort of sliding into the territory of amplitude modulation, which is where you modulate the amplitude of the carrier sound that we call, in a way to generate a more complex spectrum. You can also do the same with frequency, and that gives us what we call frequency modulation, FM synthesis, which is also used in radio. Amplitude modulation is also used in radio, of course. So this is another example of what we call subtractive synthesis. So in this case, now I have a generator that is generating noise. So it's basically some form of random signal. And then I have another operator, which is, so here it's a pink, for pink noise. Then I have another operator called BUT-BP, which stands for Butterworth Bandpass Filter. What it means is that it allows frequencies within a frequency band to pass. So it's not perfect, of course, but it will attenuate every frequency that is outside of that range. So here, both the frequency and the bandwidth are parameters. So frequency is the center frequency. The bandwidth is the range, plus or minus, where it intends to preserve the intensity. And everything is multiplied by this other operator that basically gives us a curve so that the note has an attack portion where it sort of sharply rises to its peak level, and then it decays. And then I play a bunch of notes here just to give you an idea of how changing the parameters change the quality of the sound. So frequency is the center frequency of the filter. Bandwidth is how much, besides that center frequency, we are allowing to pass. So if it says a narrow bandwidth, like small value, you will hear more of a pitched sound, because most of the noise is going to be filtered out. If it's a higher bandwidth, you're going to hear a more noisy sound. And the last one is what we call the attack. So it's how shortly do we rise from the beginning of the node, so with 0 intensity, to its peak, so its top intensity. So let's hear like the effect that this has. Maybe. I think that's probably too much. So the last ones had a narrower bandwidth, so you hear more of you start to recognize a pitch there. It's not just wind-like sound. And also because they have a shorter attack, they feel more percussive, like a snap, because they quickly rise to the peak volume. Whereas a longer attack will sort of give you a sort of a slide feeling, a crescendo feeling. Yeah, so these are the sort of things that, as you're starting with digital synthesis for sound production, these are the things that, the types of experiments that you would do, like whatever software you're using, either a programming language or maybe something with a GUI or even analog hardware. Yeah. Okay, so this is a little bit of the syntax of the underlying representation for the, so coming back to programming language. The syntax of the, how we represent the expressions in OCaml. An important part here are the opcodes. So opcodes, they match to instructions in Csound. They each carry their own ID, and this is both for performance and correctness, because if I have one source of sound in my instrument and it's used in multiple places, I don't want to create 5, 10 oscillators. They need to be the same original one, both, as I said, for performance, but also because if your signal generator is non-deterministic, it actually will give you a different sound. And the block, which, if you remember, is what the instrument takes as a parameter, basically carries a list of commands, the set of IDs that it contains. And these are used because we expose this block through a monadic interface, and this allows us to keep track of the proper sequencing of things and deduplication of shared dependencies between different terms. So this is an example of how it's of compilation. So the thing on the top is very similar to an example that we had, and the thing on the bottom is basically Csound syntax. It's auto-generated, so it has extraneous parentheses, and the variable names are not that good, but Csound is a language that you actually work with directly, and it's actually pretty nice. It's, of course, more or less focused on sound synthesis. It's not general purpose programming. Another example, this one is basically playing a file, so a sound file. Something that this example shares with the previous one and all the ones that I have played is that it's using the out-p operator. But if you look at the result of the compilation, this is actually not present in the compiled code. And the reason is that this is already an abstraction that I'm providing, or that the library is providing, so that it compiles to a use of the pen-to operator and then the out stereo operator in Csound. So this sort of serves as a demonstration that you can, as I said, use OCaml as the meta language and build abstraction that would be, at least for me, harder to do in Csound by itself. Okay, and then this takes us to the next topic, which is the other library that is sort of part of what I'm demonstrating, which I have called Melvin, standing for ML Live and Interactive. And it's a library to do communicating concurrent processes in OCaml. interactively so that you can reload code at runtime. The processes are always related. There's some facility for storing data dynamically so that it persists and accessing it dynamically so that it persists across code reloading. It has some built-in things for monitoring. And my idea is that it's a bit of a low-level framework on top of which you would build more specific libraries for live coding performances. And if you're thinking, OK, this sounds a little bit like Erlang, in a sense it does, but it's not really there. These are actual operating system processes, so they are way heavier weight than what you would get from Erlang. Reloading code works well, but there are some limitations. So for example, this is a problem that you wouldn't have in Erlang, but evolving type definitions is difficult. And because it's a framework on which to build live coding performances, it's not really something that someone that wants to start with live coding could sit down and then start making music. There are libraries that are really high level and sort of well packaged together at this point that I would recommend instead of sort of my ongoing work. An example is Tidal written in Haskell. So actually, all the examples that I have shown so far were already using this library. So there was basically one running instance of the synthesizer, and every time that I evaluated it, that code was compiled, was linked, dynamically linked into the running OCaml program. And then the instrument definition would be executed, and everything would happen. So what was actually happening under the hood was that there's a control program, which I call Melvin C. It's executed, reads the project configuration. It acquires a lock so that it's the only thing that is making changes. It does some scaffolding of the project if it doesn't exist yet. Then it compiles the new version of the code that you're submitting, and it executes it. The control program executes it and keeps track of what nodes would be affected by that program. It sort of inspects the working directory to know what nodes are running, and then forks processes to start the ones that are not running, sends a message to the ones that are running saying, OK, there's this new piece of code that you need to execute, and then sends messages to the other node, to the nodes that need to be exited, need to be stopped. This node is being affected. This node is being stopped. So it knows what things are going to be touched, what needs to be updated, and then it knows who to contact to upload the new code. Whereas the actual nodes that are doing things, they're actually working, they execute the code, then they iterate over the queue. They pass their own implementation of this module, and execute only what is relevant to them. So if I'm the node player and I see, OK, this needs to be executed on the node player, I execute that function. But if there's something that is sort of surrounded by a node call that pertains to a different node, then that particular one just ignores it. OK. Yeah, I think I went too long on the examples. So there are some facilities for basically what we call like something like universal types, so that you can encode values dynamically, so that you can then pass as messages, so that nodes communicate. There's some facility for dynamic storage, so that you can persist values across reloading of codes. And my final example was that the synth node that I'm using to play things is just one more node for Melvin that carries the instance of the sound, the synth library. Yeah. So my future plans for this is to expose more synth features. C-Sound has more features that I'm not exposing that can be useful. Is to integrate with video so that I can live code video as well. And then, in general, make more use of pieces of the OCaml ecosystem that I'm not using that could be useful, and increase the number of things that would make it easier for people to get into it. Yeah, I think that's it.